Now let's talk about modifying matrices. Like subsetting, matrix modification is an extension of vector modification, though there are some additional functions that are specifically for working with matrices. Let's put my matrix back up. Here it is. You can use subsetting to modify a matrix just like you can a vector. So here, I'm looking at row 2, column 2. Currently, there's a 14 there. I'm going to change it to a 17. Now let's look. It's been changed. Here, I'm going to change an entire column, column D. I'm going to use the name to change that, and I'm putting in the vector of 14, 22, and 10 into column D. There it is. Here, I'm going to change based upon row and column selection. Row 1, row 3, column D. Those are two numbers. Currently, row 1 and 3, column D have a 14 and a 10. I'm going to change them to 15 and 11. Mathematical operations can be used on matrix elements. Here I'm going to take row 3, and I'm going to change it to what row 3 originally was, plus 1, 2, 3, 4. So row 3 currently has 25, 14, 19, and 11. I'm going to add 1, 2, 3, 4. And now it's 26, 16, 22, and 15. If we just use a scalar rather than a vector, the scalar math will operate on all the selected elements. In this particular case, for example, I'm going to multiply the entire matrix by 2, so everything in the current matrix will be multiplied by 2. Here I'm going to take the column A, and I'm going to add 5 to column A. Notice that because I did not specify any particular position to add the 5 to, it added it to the whole column. Whatever I select as what I want changed, that's what the scalar will be added to. Rows or columns can be added using rbind or cbind. So let's go ahead and create a vector E, and now use cbind to add it to my matrix. Now my matrix has a new column. If I want, I can change the dimensions of a matrix with the dim function. So currently we have a matrix that's 3 by 5, 3 rows, 5 columns. Let me change it to 5 rows, 3 columns. Notice the order in which it was done. It's done by column. So if you think of this as a vector, 35, 49, 57, 18, 34, 32, notice 35, 49, 57, 18, 34 is in the first column of the new matrix. And then there's matrix transposition. To transpose a matrix, use the T function. Transpose means let's make all the rows columns and all the columns rows. So take a look at what we have here right now. 5 by 3, and the first column is 35, 49, 57, 18, 34. And once I transpose it, now it's a 3 by 5, and the first row is 35, 49, 57, 18, 34. So to review, we can assign to places in the matrix and change those places using the subset function. We can do mathematical operations to modify a matrix. We can add rows with rbind or columns with cbind. We can change dimensions with the dim. And we can transpose with the T. Now, if you're wondering, why would I ever want to do that? Why would I want to transpose a matrix? This gets into the usefulness of matrices in statistics. Matrix operations are actually at the core of most statistical functions. Understanding how to calculate statistics with matrices is a major leveling up in statistical expertise that reveals a new world of analysis. In fact, many people who are going to get very much in the weeds with statistics, including both mathematical statisticians and quantitative researchers like myself, will actually take courses in doing statistics with matrices. So what I'm going to do now is give you a little flavor for statistics with matrices. I'm not asking you to remember anything of what I'm showing you, but I do hope it whets the appetite for some of you. R and every other well-known statistical package on the planet uses matrices behind the scenes to perform statistical operations. The purpose of this section is to demonstrate the calculation of statistics using matrices. And like I say, not only statistical software, but researchers who really want to get in the weeds in understanding how statistics works actually learn it through matrices. So I've cleared the console and I've cleared the environment, and now I'm going to begin by scanning in some data using the scan function. You should take a look at my scores.txt file to see what it looks like. It's just a list of numbers, and you can use scan to read in simple text files. So I'm going to specify that I'm going to have 100 numbers. I'm going to read that in. And now what I'm going to do is put it in standard matrix format with individuals in rows and variables. In this case, it's just one variable in a column. So I'm giving dimension to that vector, so it now has 2 dimensions. Let's go ahead and look at score. There it is. 100 rows, 1 column. I'm also going to create a vector of 100 ones. This is known as the summing vector. I'm going to turn that into a matrix as well. So notice that I'm using the repeat function to give me a 1 100 times. You can see this here in the environment, the first part of that. And now I'm going to give it dimension. And so now it comes up here into the data because now it's 100 rows with 1 column. For any score vector, x, we can obtain the sum by taking the transpose of our 1 vector, and 1 prime is how we indicate transpose, and multiplying it, not scalar multiplication, but matrix multiplication by x. So here I'm getting the score sum. Let's look at what we got. The score sum here, it says, is a 1 by 1, 4954. Let's actually do it the way we're used to, taking the sum of all the score vector, and we get 4954. So you can see that I can get a sum by taking the transpose of a matrix times a matrix. The mean is given then by just pre-multiplying this matrix product by 1 over n. So if you look at here, I'm taking 1 over n times the transpose of 1's, matrix multiplied by score, and that gives me, you can see in my environment, 49.5. Let's do it the normal vector way that we're used to, 49.54. So far, so good. Now it's a simple step to deviation scores via matrices. All we have to do is take our score vector minus 1's matrix multiplication times the score mean, and we get the deviations. So here are the score deviations now. Let's go ahead and look at those. There they are. Those are all the deviations from the mean. And now I can calculate the sum of squares by taking the transpose of those deviations and matrix multiplying it by score deviations. That is, I'm multiplying deviation by deviation, which is what sums of squares are. So let's look at this. There's the sums of squares. I could have gone straight to the variance. How? By simply pre-multiplying by 1 over n minus 1. Remember that to get the variance, we take sums of squares and divide it by n minus 1. So that's what I'm doing here. So if I look at score variance, there it is, 91.8. Now I'm going to get into really the way statistical programs do this. I showed you some simple matrix operations, and if you don't think it's simple, it's okay. You don't have to know this. But for any of you who want to really get into it, I'd recommend and encourage you to explore it. But watch this now. First of all, I'm going to calculate a matrix filled with 1 over n. I'm doing this by taking 1's matrix multiplied by the transpose of 1 and dividing by n. That gives me this P matrix. Let's take a look at that P matrix. There it is. So I have a matrix filled with 0.01s, which is 1 over 100. Now I'm going to calculate what we call the identity matrix. The identity matrix has 1s in the diagonal. Let's look at it. There it is. See, the 1s are in the diagonal of the matrix. Everything else is 0. This is called the identity matrix because if you multiply it by any matrix, you get back the original matrix. Just like if I multiply a scalar by the number 1, I get back the original number. So let's take the identity matrix and let's matrix multiply it by score. What we end up with is the same thing we had with score. Now I'm going to calculate what is known as the projection matrix. And that is calculated by taking the identity matrix and subtracting P. Remember what P looked like. P looked like, we still have it here, it looked, oh, I just deleted it. P looked like a matrix filled with 1 over n. So I'm going to take that identity matrix and subtract that matrix filled with 1 over n. Seems like a simple thing. And that gives us a projection matrix. And you say, why? Why bother with a projection matrix? Watch what happens when we pre-multiply our scores by the projection matrix. What did I end up getting there? I ended up getting the deviations. Pre-multiplying by the projection matrix, the score gave me deviations from the mean. Pretty wild, huh? We didn't even think of the mean as being involved in this. Now here's another cool operation. I'm going to now take 1 over n minus 1 times the transpose of my score matrix times the transpose of my projection matrix times the projection matrix times the score. Let's see if we recognize this. Do you recognize that number? It's still down here in our window. That was our variance. So this gave us our variance. Let's read in a couple more variables and add them to our matrix. So now I have score 1, 2, and 3. I'm going to bind them together. Let's take a look at that. Here's our data, 100 individuals, and now we have 3 scores for those 100 individuals. I'm going to take and create our data divs by taking the projection matrix times our data. And let's look at our data divs. It is the individual deviations from the mean for each of those scores. Now I'm going to take 1 over n minus 1 multiplied by the transpose of our data multiplied by the projection matrix multiplied by our data. And what I get here is a variance-covariance matrix, where variances are on the diagonal and covariances are on the off-diagonal. So the covariance of score 1 and score 2 here is 57.8. One more cool one. First, I'm going to take those variance elements out of our matrix by taking the diagonal elements out of our covariance matrix, and I'm going to divide the square root of that into 1. Now I'm going to create a diagonal matrix of that. This is what it looks like, so that I have zeros, and then all I have are my variances in the diagonal. That's all that's there. And now watch. I'm going to take that diagonal matrix, do matrix multiplication with the covariance matrix, and then again multiply by that diagonal. And what did we get? That's a correlation matrix. We just calculated the correlation among all three of those variables. So again, if your mind is blown, if you're saying, what the heck? Or, do I have to remember this? The answer is no, you don't. But if you ask the question, what is the usefulness of matrices in statistics? I'm trying to give you a little flavor, and let me assure you, it goes much deeper than this. It goes into everything we do with factor analysis. It goes into structural equation modeling. It goes into analysis of variance. It goes into multi-level models. And in fact, all the statistical packages, when they provide you output for even something as simple as a variance or a t-test, it's actually doing matrices behind the scenes, just like you saw me demonstrate right here.